All right, hello, sensation and perception class. Dr. Tausman coming to you live from my windy house here in Roanoke, Virginia on a Sunday night, 2/12/2017. Happy February to all of you. I wanted to start off actually with giving a little bit of a presentation. I have an agenda on neuroscience. It's going to be a bit of a review for some of you, but I want to make sure we're all kind of on the same page. So what you might want to choose to do when you're writing out your detailed outline of this information is use the agenda and just type in detailed notes that are structured, have all the right content in them. The first place I wanted to start is actually some philosophical issues in biological psychology. And one of the big issues that has confronted a lot of people has been the relationship between mind, mental, physical, emotional states, and body, the physiology, the neurotransmitters, the chemicals, and the pathways that dot us going up to the brain, basically. And there are basically two types of positions you can take on this. Descartes was one of the early philosophers who said, you know what? Mind and body are completely separate. Psychology, philosophy people, you guys deal with the mind. Leave the body stuff to the doctors and the medical people. So Descartes basically believed in dualism. Mind and body are completely separate, and there's really no link between them. We now kind of don't really buy too much into that dualistic perspective. Instead, we believe that there is some sort of relationship between mind and body. Certainly, if you've taken medications before, you know that medications affect the body and then can affect the mind as well. So most people believe in some form of monism, that there is a relationship between mind and body. There are two different types of this. One type is called type reductionism. And in type reductionism, you believe all mental states can be reduced to neurobiological underpinnings, that there's a one-to-one match between mind and body. As you'll discover as we go through this visual unit, many years ago some researchers discovered that there seemed to be neurons in monkeys' brains that only fired when certain faces were being shown. And so if you showed one face, one neuron would fire. If you showed another face, another neuron would fire. These cells were called grandmother cells and seemed to indicate kind of the type reductionistic idea that one face, one neuron, a very one-to-one reductionism going on. Many people, myself included, don't necessarily take that position. We believe that there's something more called token reductionism. We believe there is a link between mind and body, but it's not a one-to-one match. And I think our best example might be the disease that is known as depression. We know that depression is linked to low levels of serotonin, but we also know that just fixing levels of serotonin at a body level is not going to fix the mental state of depression at the mind level. That there is some sort of relationship between mind and body, but it's not one-to-one. So that's the philosophical issue that we deal with first. Next, I wanted to just make sure that we were all on the same page as far as how neurons actually work, because we're going to come across this in the many units we have in this class. Neuronal activity. Just to give you the overview of things, dendrites collect electricity. They collect electricity, and if you collect enough electricity, that's considered 15 millivolts of depolarization. I think that's somewhere in your book. If you collect 15 millivolts at the dendrites of depolarization, they will summate at the cell body. So if you have three different little trees growing out, and each one of them collects 5 millivolts of positive depolarization energy, then you will actually initiate an action potential. And that action potential will go down the axon, insulated, if you look at that first picture I have, by the myelin sheath, regenerating the action potential at the nodes of Ranvier as it goes down the axon. The myelin sheath is very helpful for people that don't have working myelin sheath. They have multiple sclerosis. So we know that information about neurons and how they basically work. Let's see, and then at the end of the neuron, the next picture kind of shows a picture of the synapse. That's a little gap between neurons, and then there's a gap there. Then there are the dendrites of the next neuron. So in terms of the electricity, we know a few things before anything happens to the neuron. For the neuron, before anything actually happens to it, we can look at its electrophysiology. The electrophysiology is basically the idea of how the neuron is before anything happens to it. We know there's a lot of sodium outside of the membrane, and there's a lot of potassium inside the membrane. If you look at my little picture there of the lipid bilayer that separates the outside of the cell from inside, a lot of sodium outside, a lot of potassium inside. The other thing we know is that inside the neuron there's a negative 70 millivolt charge. And then the final thing we know, the fourth little fun fact, there's a little sodium-potassium pump that kind of keeps the sodium outside and the potassium inside. So in order to start an action potential, what needs to actually occur is you need to collect those 15 millivolts of depolarization. If that's done, a signal will be generated right at the start of the axon. It's called the axon hillock, Hillock. And at the axon hillock, an action potential will be created, and it'll basically be sent down the axon through saltatory conduction, kind of point-to-point conduction through these nodes of Ranvier. The reason this is done is just to save energy. If the action potential is recreated at every point, axons can be very long, for example in giraffes. So it's better to save energy and send them along in this point-to-point communication. So hopefully that makes sense to you and you understand that reasonably well. The other part of the story I wanted to share with you is what happens at the end of the axon. As it turns out, at the end of the axon, the electricity kind of stops. And in between one axon of one neuron and then the dendrite of the next neuron is a synapse. And so it's really more of a neurochemical process that happens there. So for neurochemistry, a neurotransmitter has to be synthesized. Could you eat serotonin, acetylcholine, dopamine, norepinephrine, and epinephrine? Yeah, you could, but they wouldn't cross your blood-brain barrier. So instead, we eat precursor chemicals from our diet, and they are converted into neurotransmitters. Milk has a lot of tryptophan in it. Tryptophan is a precursor to serotonin, as an example. So the neurotransmitter is stored in vesicles. The neurotransmitter is made, synthesized. It's stored in vesicles, and then it's released. The process of release is another picture I drew there called exocytosis. You actually need, this is very important, the process of exocytosis. The neurotransmitter in its vesicle fuses with the membrane. In order to get this to occur, this is where the action potential actually causes this to happen. So this is where the electrophysiology story fuses with the neurochemistry story to cause a release of the neurotransmitter. So release is step 3. You also need calcium there for exocytosis to happen. Then the neurotransmitter travels across the synapse. As the old Doors song used to say, get on to the other side. It travels across the synapse, and then it binds basically on the next dendrite. The spot on the next dendrite that it binds to is called the postsynaptic receptor. And there are 2 ways that neurotransmitters actually cause their functioning postsynaptically. The first way is the neurotransmitter binds and opens up a channel immediately. That's called ionotropic. The second way is the neurotransmitter binds and then sends a second messenger like cyclic AMP to open up another channel. And the difference between these 2 mechanisms is ionotropic happens quickly but is relatively short-lived. Metabotropic takes a little longer time but lasts a little bit longer. So that is the binding that actually takes place. And when the binding takes place, just to give you a real-world example of this, when the neurotransmitter glutamate binds, and when it binds, it'll allow calcium to come in postsynaptically. Calcium is Ca++. That'll actually cause a big depolarization postsynaptically, but instead of calling it depolarization, we call it an excitatory postsynaptic potential, or EPSP. And then that'll lead the next neuron to have an action potential. On the other hand, GABA, GABA, which stands for Y-aminobutyric acid, you don't need to know that. When GABA binds, it tends to open up a chloride channel, and you get a chloride influx. chloride is Cl negative, and that'll tend to inhibit another action potential. And if you're wondering, well, why would you want to ever inhibit an action potential? Well, the answer is actually very simple. When people have anxiety disorders, they take Xanax and Valium. Those products actually reduce anxiety by getting GABA to work better and causing IPSPs. So we have these IPSPs, these EPSPs. They actually send the signal and continue the signal. And then if you watch the video, you can see a little more. The last step is called inactivation of a neurotransmitter. This happens one of two ways: an enzyme that can come in and destroy a neurotransmitter, or the neurotransmitter can be taken back up, reuptake by the neurotransmitter. So hopefully that makes good sense to you, and I just wanted to share that as kind of backup information before we get into a few more details here. Actually, I have a little more time here, so I'll do a little bit more. This will tie in a little more to the sensation and perception class. If you look at the Roman numeral there, and I put the wrong Roman numeral there because I have 1, 2, 3, 4, 5. This should be number 6, I think, here. For Roman numeral 6, which is sensory information and the steps, the idea here is, look at that problem there I wrote, 100 plus 25. What is going on to allow you to do that problem? You all probably verbally said, that's 125. Well, there are actually a lot of steps involved with that. The first step is the light energy, and you may want to write these steps down. The light energy has to hit your eye. That's step 1. The light energy hits your eye. Step 2, described on page 47, is the light energy is actually changed into action potential energy, electrochemical impulses. That is called transduction. And so transduction happens in your eye from the rods and cones that are in your retina. So they do that. That information then goes up, especially if it's visually, to your optic chiasm, and then that'll enter your central nervous system. And in your central nervous system, it's divided into 3 general areas. We have the hindbrain, midbrain, and forebrain. The hindbrain, that controls basic primitive functioning. The cerebellum, if you've had any alcohol to drink and you can't keep your balance and move straight, that's the cerebellum, so that's movement. The pons is in charge of kind of arousal things, waking up in the morning. The medulla, kind of call the medulla the 7 dwarfs area. Sneezing, coughing, well, I think only sneezy was in there. Coughing, respiration, breathing, all those kind of automatic voluntary processes. Throwing up, spitting up, whatever you want to call it. What, reverse peristalsis? That's the medulla. The midbrain contains the substantia nigra. That has a lot of dopamine in it. When people get Parkinson's disease, they lose a lot of dopamine up there. The periaqueductal gray, that's right around the cerebral aqueduct. That contains a lot of your brain's endorphins. So when you take morphine, it's actually going up there and helping with pain. The superior colliculus controls visual eye movements. When you follow people around, the inferior colliculus just, it had an inferiority complex about the superior one. No, I'm just making a joke there. Bad joke. The inferior colliculus is in charge of following sound when people are moving. In the forebrain, we have 2 general areas, the subcortical area, and the main structure there that you're going to learn a lot more about in this class is called the thalamus. The thalamus is kind of the relay station of the brain. When anything comes in through your rods and cones, it goes to the optic chiasm, and the first structure it reaches is the thalamus. From the thalamus, it can actually go to the cerebral cortex. Visual information goes to the occipital lobe, sound information to the temporal. The parietal lobe actually has a lot of the touch areas of your body, and then the frontal lobe is more with attention and higher level cognitive processing. The other structures that it can go to from the thalamus are the other subcortical structures. The hippocampus is with memory, the amygdala is with anxiety and emotion, a lot of Xanax receptors there, and then, GABA receptors there. Then the hypothalamus is in charge of the endocrine system, which gets all of your hormones going for basic things like temperature, sex, eating, drinking, and so forth. So that is the divvying up of the central nervous system. that all of you should have some basic understanding of. Hopefully this makes sense, and this is kind of the neuroscience review. Thank you all very much. Bye-bye.